In this video, we'll be looking at a topic called finding the value of c when doing antiderivatives. This is sometimes called finding the particular solution for a differential equation, and we'll be looking at it through the context of particle motion. First, a bit of review. Let's take a look at this classic antiderivative problem. We're asked to find the antiderivative of ln quantity x squared over x. I encourage you to pause the video, see if you can make sense of this problem, and come up with a solution before we reveal how it's actually solved. As is often the case, rewriting the antiderivative, or the integrand rather, is a useful good first step. So if we write it in this format here, where we recognize that there are two major components, or really three major components of its problem, we'll see that we have 1 over x, we have the quantity ln of x, and the entire quantity is being squared. So when I say three operations, there's basically this portion here, and then the overall idea of squaring something. So 3 bits altogether. Hopefully this is ringing a bell as being a reverse chain rule problem, in the sense that the derivative of the inside part, or the inner part of the composite function, its derivative is chained on next to it, because ln of x's derivative is 1 over x, and that's precisely what we see. So all smiles in the way we look at in class. Which means we can effectively ignore the chain, because as we roll back the clock, we know the 1 over x will pop out from the ln of x's chain rule derivative. So we basically have some quantity being squared. So now we can use the reverse power rule, which is to say if a quantity squared is the antiderivative, then that very same quantity raised to the third power divided by 3, or multiplied by 1/3, either way, should be the antiderivative plus a constant. Which, if we sort of mentally check our answer, this 3 would come down to take the power rule derivative, and then this would stay ln of x, and then squared, and then 1 over x gets chained on, which precisely is our integrand. So just a little bit of review. But let's look at finding c in detail. First, it's important to recognize that the solution to an antiderivative problem, which is one reason I gave the review question here earlier, is not a single function. If we look back for a moment, this is not a single function, but rather an entire collection of functions, all of which are linked together by this plus c, which is sort of a thing of convenience. We haven't really talked a whole lot about what purpose it serves, except for a little bit graphically, but we'll be dialing a little more in that area here. But the solution to an antiderivative here is a family of functions, an entire set of functions, not just a single curve, but a variety of them. And graphically, we can look at them in this manner here, where if the solution to an antiderivative, like let's say this was 2x and we get x squared or something like that, then all of these parabolas have the exact same derivative, the same tangent line slope at any given point. And the plus c could be the vertical translation that indicates that if you shift the function up or down, the slope at any point remains the same. So for a given x value, like let's say right here, whatever this x value is, the slope of all of these parabolas are identical at that x value. And that's what the plus c is indicating. And the same is true for these periodic functions as well. In order to actually pick out a single solution from this family of functions, what we need is an additional piece of information. In fact, specifically what we need is an additional point, a single point through which the function must pass. So if you think about this as being the family of functions that is a solution to some antiderivative, if we knew that the function in question had to go through a single dot, then we know that the particular member of this family that satisfies the antiderivative and passes through that dot would look something like this. It mimics all the other ones in its family, but the plus c we can actually single out and define exactly what that is. Let's look at this in practice. Here we have a deceptively, I don't want to say a simple looking problem, but one that's fairly innocuous at first. It actually has quite a bit of meat to its bones. It says moving object has an acceleration modeled by this function, 2 sine 2t feet per second squared. The question is, where is the object at time t equals 3 if the initial velocity is 4 and the initial position is 2? So right away, hopefully you're remembering the motion hierarchy, which is the manner in which the position and velocity and acceleration relate to each other. You'll notice the question asks for where is the object, and where is an answer, or is a question that's answered by position. What we're given is acceleration. Where something is its position, its acceleration is how quickly that rate of change is changing. So to review, the motion hierarchy looks something like this. Let me uncover this properly. Where to go in the forward direction, the way we have been doing until now, you take derivatives, and you can, with respect to time usually, and you can arrive at the lower level function. So since an antiderivative is defined to be the inverse of a derivative, it naturally makes sense that you can antiderive and move backwards from acceleration to velocity and from velocity to position. So we're moving up the hierarchy as opposed to down the hierarchy as we had been before. So let's look at the actual math here. As mentioned, the actual question is, what is the position at 3? And we're basically 2 levels of extraction away from the position function, so we need to work our way up through velocity to eventually get to position. We'll first recognize that acceleration, a, is given right here, is defined as the change in velocity over the change in time. That's what acceleration is by being the derivative of velocity. We're going to do something a little unorthodox here in that we're going to split apart this dv dt, this change and this ratio of change in one thing over change in another. I'm effectively going to multiply both sides by dt. In so doing, the left-hand side will just become dv and the right-hand side becomes this. So hopefully you can see where one goes from here to here. I'm going to do something a little more unorthodox, which is to say I'm going to take the antiderivative of both sides. So we just have the same step indicated here. I just copy-pasted it. I'm going to antiderive both sides. Now, it's something we haven't done before. We haven't done the antiderivative as an operation, but just as limits are operations and just as derivatives are operations. An operation is something you do to a mathematical statement. If this red statement, the change in velocity, is equal to the this function times the change in time, then the antiderivative of both sides should also be equal to each other. And you'll notice that the notation here actually works out nicely. By design, an antiderivative, which is the blue symbol, and the derivative, so to speak, the d symbol here, will cancel, leaving you with just velocity, or v, for the left-hand side. And on the right-hand side, you have literally an antiderivative problem. You have, what is the antiderivative of 2 sine of 2t dt? And the dt is there sort of as a notational thing for the limit of, for the variable of integration. And hopefully this is also ringing a bell as a reverse chain rule problem. 2t is the argument of the sine function. Its derivative is 2, which you'll notice is already next to it, so all smiles here. We can ignore the 2 and just focus on the sine function. Sine is the derivative of, let's see, cosine's derivative is negative sine, so negative cosine's derivative should be positive sine. So I just took the antiderivative, get this out of the way for a second, the antiderivative of this statement right here would produce this plus c. So the velocity function we got from the acceleration function is right here in red. However, we can go a step further because it's told to us that the initial velocity is 4 feet per second. The initial velocity is 4 feet per second, which means we can take this piece of information that we just anti-derived in tandem with that information that was just given to us. The initial velocity is 4, which means the velocity at time t equals 0, hence the idea of initial time, 0 time, is 4. We can use that information and plug in this to be 4 right here for velocity, the time to be 0, and the only missing part would be c, which means we can find c. So if we do so, we have the velocity at 0, which is 4, and the velocity at 0 means we plug in 0 right here. So if we do that, the cosine of 2 times 0 is the cosine of 0, which is the cosine, which becomes 1, and there's a negative out front, so that becomes negative 1. And double check me on all that if you're a little rusty on your trig. But that should be negative 1 plus c, which means the c value in question here is specifically 5. So we took the family of functions here in red in combination with the given point 0, 4. Together those allowed us to find c, which means that the specific velocity function is this guy right here. In general it's red, but in particular it is this green function. However, our actual question is what's the position at 3? So essentially we've gone up the scale here to this level. We still need to go up one more level to position to get the position function. But that's not a problem because velocity, recall, is defined as the change in position over the change in time. So based on that formulation, I'm going to replace the velocity with its derivative interpretation, the change in position over change in time, and just repeat the process. So multiply both sides by dt. That'll give me this formulation here. Integrate both sides. integrate both sides. These cancel, giving me just position, because an antiderivative of the derivative will just give you the variable here, which is position. And here I have a somewhat more complicated antiderivative, but nothing harder than what you've done before, most likely. I'm going to treat each part separately, so this 5 will spawn a fairly straightforward 5t. Hopefully that's not too bad. You can see that in just a moment. But let's focus on this part right here. The first thing I'm going to do to make this easier on myself is I'm going to factor this negative constant out. So I just brought that negative out front here. Cosine is the overall function, but the inner function here is 2t. The derivative of 2t is 2, which I don't have sitting next to it until I put it there. But since I'm changing the function, I'm going to modify that or adjust for that change by putting the 1/2 out here. So with that rectification, I now have the reverse chain rule, so I can now ignore the 2 because I know its origin was the 2t's derivative. Cosine is the derivative of sine. So the antiderivative of 2 cosine 2t should be negative 1/2, well, with the negative out here, should be negative 1/2 sine of 2t, which you see I have right here. As mentioned, 5 is just 5t plus c. So our general solution for the position is this guy right here in the red and blue. It's the general position function. But once again, we can find this new c value because we're also given the initial position. The initial position was that at time t equals 0, hence the idea once again of initial, the position was 2. So if you plug 0 into the function and set that equal to the output, which is given to us as 2, let's see, sine of 0 is 0 times 1/2 is 0, 5 times 0 is 0, so 0 plus 0 gives us just c on the right-hand side, and 2 for the other side, so that's a pretty straightforward one because this all vanishes, giving us just 2. So the new and improved particular version of this general position function, the particular position function is this right here. We moved from acceleration to velocity, found the value of c, which gave us the particular velocity function. We integrated that with the initial position to find the particular position function, which is right here in this underlined form. You notice the only variable is t, the only independent variable here is time because we have found the value of c. To close this out, the actual question said, if we scroll back through all this work, where is the object at time t equals 3? Well, that was unknowable without knowing the position function, but now we know the position function, so now the question is simply, well, you've made this new tool to find where a thing is at any given time, use it to find where the object is at time t equals 3. So just plug 3 in, you get this statement right here, for pretty obvious reasons you can see. And that doesn't work out very nicely because of sine of 6 being sort of a decimal, but in the calculator you can find this will produce a value of approximately 17.14 feet. So from measuring an object's acceleration in tandem with its initial descriptions of its initial velocity and its initial location or position, we can use calculus to figure out where that object will be at any given time. It's actually a big leap in terms of physics. You can study how an object is accelerating along with how it's moving initially and predict where it's going to be at any time in the future, namely 3, but in general, anytime you want. So to summarize, to find c, simply take the antiderivative as you have been doing and use the given point, which we did twice, to go from position, to get to position from acceleration. Use the given point to solve for c, and then you have your particular solution. And that wraps it up.